Let us quickly go through this topic once. I'm sure you have already gone through the NCRT. Mainly, I'll focus on certain points which have been, vaguely asked or how it has been framed in the exams. Okay, let's see. As much as Group 1 elements are concerned, these are lithium to francium. Okay, their general configuration is NS1. Francium is radioactive metal, and this is their general configuration. How to write it down? They all show monovalent oxidation state. Okay. This is a screen stuff. Sorry, guys, I lost the connection. Second. Yes, the screen is visible, everyone. Yeah, let's see. As we deep, as we discuss into the atomic size is a regular trend which increases down the and the Z effective remains constant from sodium towards francium. So between these two, if you remember using Slater's rule, we were able to figure out that the Z effective from here till this point will remain constant. Only the new shells has been added because of which the size is increasing. Okay. And as much as one second, as much as atomic and ionic size is concerned, right? Uh, atomic size will always increase down the group, as we can see here, like this. Increases down the group here. This way it should have been increase down the group. And ionic size depend upon whether it is gaseous or as much as the gaseous phase is concerned. This is gas phase. As much as gas phase is concerned, down the group, the ionic size will also increase. Okay. Ionization enthalpy mainly depends upon how much is the charge and how much is the size. Based on that, there is a regular trend of decreasing ionization enthalpy. Hydration enthalpy and size, if you notice, hydration energy, as we go towards downsize here, uh, if we compare the hydration enthalpy, then lithium would have the highest. Okay, so lithium plus will have the highest charge density because of its hydrated molecules, and in fact, it will exist as LiCl.2H2O. Got it? And most of the energy is released when you do hydration energy here. So therefore, now the size of the aqueous solution here, so these are aqueous ions, would decrease down the group. So lithium plus will have the highest charge, then sodium, potassium, rubidium, and cesium. Okay, this is the hydration size. So one second. Visible now? Check this out. So hydration enthalpy would vary this way, and aqueous ions would be this way. Lithium towards cesium, it will decrease. Got it? And this is the size of the hydrated ions. Now, as much as physical properties are concerned, all of these metals are soft, silvery white, and melting point, it will decrease down the group because of the softness. It will start decreasing down the group. So you will see this is the melting point order. I'll just mark it down wherever an important trend is coming. This is one important trend. It's how the melting point varies. Okay. Next, density, small exception is observed here. So exception here is this one. You can see lithium towards cesium. If you notice, this is the exception where cesium is more rubidium, then sodium is more than potassium than lithium. Okay, and most of the metals are highly reactive, so they are either kept in kerosene except for lithium. Okay, lithium is usually kept in paraffin wax. Okay, now due to the low density, lithium floats on kerosene. That's why it should be stored in paraffin waxes. Yeah. Next, usually whenever we have Bunsen burner, you know that this is the oxidizing flame where air is more, fuel is less. Here, fuel is more, air is less, that is reducing flame. Okay. And when it comes to uh, flame test, okay, you will see respective colors observed in these cases. So I would suggest remember this way. Okay, lithium, correct? Then strontium, calcium, rubidium, potassium will be same, barium and sodium. Okay, right. So you can see the colors here. So colors here is lithium, strontium, calcium, correct? They would have here crimson red. Okay, these are all crimson red. And then we have brick red, red violet for rubidium, lilac for potassium, barium, apple green, and sodium gives golden yellow color. Okay, these are the colors you should know. Beryllium and magnesium would, give just shiny white, and no other colors are observed in this case. Okay. Next, next important part in this case is the standard reduction potentials here. So you can notice the standard reduction potentials of lithium being, or reducing nature. I'll write it as reducing nature. So if you compare the reducing nature, lithium has the highest, then comes cesium. Okay, sorry, by data it is rubidium, then cesium, correct? Then potassium, and then sodium. Okay, these three are considered to be almost same, and then comes sodium. This is the reducing nature as much as these metals are group 1 metals are concerned. You should always see reducing nature based upon three factors. Lithium converting into Li plus aqueous. First, it should sublimate. After that, it should undergo ionization. And from there, it will undergo hydration. So these three energies will tell us, these three energies will tell us whether it will be more oxidized or whether it will remain more reduced. Okay. Next, notice that reactivity towards N2 and O2. So Usually when it comes to N2, it will first convert into N and towards N3 minus. Okay. So it depends upon how much for this to convert, right? You can see there are to have, you know, three electron affinities. Got it. So first one electron affinities is endothermic. That makes the other two also endothermic. So to convert these, we require a huge amount of energy. Okay. So you can see lithium when you react with nitrogen, it will form Li3N. But this cannot provide that sufficient amount of energy that cannot compensate to the lattice energy of metal nitride. Therefore, these cannot form nitrides directly. They cannot form directly with reaction with N2. Okay. When it comes to O2, O2 has to accept an electron, convert into O2 minus, O2 minus, and accepting one more electron, it will become O2 2 minus, and eventually it will become O2 minus, normal oxide, superoxide, peroxide, and normal oxide. Okay. Here it is exo, then we have endo and endo, correct? Here also we require sufficient amount of energy for it to form a stronger lattice. Lithium forms very easily. It will form Li2O, right? So if you notice lithium in air, it gives both nitrides and oxides, correct? Out of which Li2O and Li3N are major products. Peroxide is minor. While when it comes to sodium, Na2O2 is major, peroxide is major, and superoxide is minor. Potassium, rubidium, cesium, they will give superoxide as major and rest as minor. Okay. So it requires huge amount of energy for converting superoxides to normal oxide. So that these three cannot provide. Okay. So they can maximum go up to superoxide only. Clear everybody? Right. Next you see how they react towards water. Metal when you add it to water, they will immediately release H2 gas. They liberate H2 gas and convert themselves into hydroxide. Okay. Now, even though electronegativity wise, electron reduction potential wise, lithium has highly negative value. It is not as rigorous as that of sodium or other elements. Okay. This is because of the tiny size and very great hydration. This is because of its tiny size and great hydration energy. Okay. Remaining elements of the group react explosive with water. They react with proton donors like gaseous ammonia, alcohols, and alkynes also. See, first, like I said here, this is what we will check out for identifying the uh, oxidation of metals. So metal, when you add it to water, this is what we expect. Okay, as the ionization decreases, the rate of reaction will always increase. So kinetic reactivity, that means how faster it will undergo. That depends upon how low their ionization energy is. So therefore, the kinetic reactivity is like this. Okay, so remember that in water, this is the kinetic reactivity. That is, cesium will react faster, and as you go towards lithium, it is slower. Okay. While if it comes to thermodynamic reactivity is about checking out the complete conversion of metals. This we just learned it that it depends upon the E naught value, reduction potential value. So this is the thermodynamic reactivity. It is not about how fast the reaction is happening. It is about how stable the compound is forming. So most stable compound will be formed with lithium, right? Because of its very strong hydration. Just a minute. Next about the reactivity with halogens and hydrogen. If they react with H2 directly, correct, they would form metal hydrides. Okay. C. But you require high temperature. Got it? These metal hydrides, first group hydrates are ionic solids. They have a high melting point. Their stability decreases down the group. Okay. The reactivity of the first group with halogens result in uh, halides. Okay. This is also a rigorous reaction due to small size. Polarizing power of lithium is higher, and due to high polarizability of I minus, it will show more covalent nature. Okay, so they will all form metal, halides. See, metal plus X2 will form M plus and X minus. Okay, so it all depends upon which one has more lattice energy. If the lattice energy is more, that means it will have more ionic character. If it is less, it will have more covalent character. So ionization energy is inversely proportional to how much amount of the released energy here. So order of energy release, if you notice that, okay, LIF will release huge amount of energy. So that makes it very strong lattice compared to NAF, KF, RBF, and CSF. Okay. So if you notice the metals here, depending upon the ionization here, chloride, bromide, iodide, and hydrides, these are the ones which are formed. Okay. So usually if you have, bigger size ions, that will be more stable with cesium. Smaller size ions, that will be more stable with lithium. Got it? Check out, we discussed this already, how to understand the reduction potentials here. So the order of, reduction potentials of all these elements based on the data given is lithium greater than sodium, then iodine, then silver, then Cl minus. Now, solutions in liquid ammonia. This is a very important part for exam. Okay, check. When metal is added to liquid ammonia, it will get ammoniated ions and electron will also get ammoniated. So basically, if you notice the bond polarity, water has more polarity, got it, as compared to that of ammonia. So the extent of self-ionization in water is much more than in ammonia. So therefore, first when the metal M plus will form here, lot of ammonia molecules will surround it. Okay. And therefore, this M plus will show conductivity because of its movement in the solution. Okay. Now, what is the color which you will attain? A deep blue color solution on putting alkali metals is observed. These solutions are which conducted in nature due to availability of the free solvated electrons. Okay. The electrons are called ammoniated electrons. These absorb light in visible range owing to blue color of the solution. This solution is paramagnetic and liberate hydrogen slowly creating amide as a result. So you would notice that if I take this many moles will surround N plus and Y moles will surround electron. Okay. Now, if you notice the total volume here, this volume would be greater than that of some of these two volumes. Okay. Now you would notice that initially, as the metal concentration increases, right? So first, to certain extent, the blue color rises and blue color formation rises to certain extent. Clear? After which it reaches the peak value, that is a maximum concentration where you have maximum ammoniated electrons as well. After that, it will start decreasing as the concentration further increases. The paramagnetic nature decreases and it will start becoming more into the bronze color, correct? And diamagnetic nature start increasing. Diamagnetic nature starts increasing. Okay. So what is happening here is all the metals which are there, correct? They will start making some kind of metallic bond here, or they will come out as H2 gas. Okay. As the concentration further increases, they will start becoming H2 gas here. So that is, instead of staying just as an ammoniated ion, now these electrons will take away the H plus from the solution, H plus from the ammonia here, and come out as H2 gas, thereby uh, making a diamagnetic solution because electrons will not be available anymore. Okay. The colorless solution is obtained in the above reaction. The solution obtained is diamagnetic and conducting in nature. Okay. The conductivity is because of the metal ions. Okay. So metal ions in ethanol also will do the same logic. With ammonia gas, or if it is gas, there is no other question. Just you will write it as sodamide, metalamide, and H2 gas being released. Okay. So remember, it depends on concentration and heat. Either you provide strong heat, the paramagnetism will start converting into diamagnetism, or you increase the concentration of the metal ion, they will also start converting into, first into this covalent nature, and slowly rest of the electrons which are present, they will immediately take this H plus and convert into H2. Okay. Yes. Reaction of H2. Lithium reacts with N2 to form ionic lithium. On the other hand, it will not react. Okay. With N2. Only lithium reacts with N2 to form. Sorry, this is repeated. Yeah. Sulfides. First group reacts with sulfur and results in various sulfides. While sodium, specifically sodium, forms polysulfides. Okay. Of N number 2, 3, 4, 5, 6. Okay. It will be like a zigzag chains here, forming a polysulfide cases. Okay. Crown ethers and cryptands. Okay. So sodium metal ion will also form, crown ethers like this. So when you have sodium, um, here if you notice that in these cases, dibenzo 18 crown 6. Okay. So this is dibenzo. And then we have 18 crown 6 here like this. Okay. 18 crown as in 18 membered ring. Got it. 6 as in 6 oxygens present in here like this. 6 oxygens are present in here. Got it. Now in such cases, even if you have something like cryptand where you have nitrogen and oxygen cases here, they all will be associated either with Na plus and Na minus sodide ion. They will also be present with sodide ion. Okay. Again, it is just a reference to understand that Na plus and Na minus can exist, got it, in the formation of crown ethers. Next. Yeah, just go through the thermal stability once. Thermal stability of hydroxides, if you notice that, down the group thermal stability increases. I told you thermal stability, you look out in two cases. One, whether it is a single atom anion or whether it is a multi-species anion. OH minus is a multi-atomic anion. Multi-atomic anions down the group always thermal stability increases. Okay. Now solubility depends upon the size. Smaller the size, solubility increases down the group. OH minus is smaller in size, so solubility will always increase. Basic nature will also increase as the solubility increases. Okay. So this is the trend of OH minus. Got it. Now checking out Na2O preparation, sodium when you react with O2 at around 180 degrees, you will get Na2O. And thermal exposure of peroxide with more Na will also give you this important reaction, guys. Remember this reaction. Na2O2 plus sodium gives 2 Na2O. Okay. NaNO2 plus excess of sodium will also give you Na2O. Same logic here also. Okay. It is a white amorphous mass. On strongly heating, it will convert into peroxide, as peroxide is more stable than the simple oxide. And on adding to water, it will convert into NaOH. Okay. Next. Sodium peroxide, sodium plus O2, if you react it, where O2 is sufficient enough, then it will mainly give you peroxide. And it can give at around 300 degrees centigrade. It is pale yellow solid. Remember, it is pale yellow solid. It becomes white in air, forming Na2CO3 and NaOH. Okay. In cold water, it will produce H2O2. But at room temperature, it produces O2. Okay, so you can see Na2O2 plus H2O will form NaOH and H2O. But if it is around room temperature, that H2O, basically H2O2 is formed that will decompose into H2O and O2. Okay. And with H2SO4, it will form Na2SO4 and H2O2. Its acid-base reaction with carbon dioxide is the reason why it is used to purify confined spaces like submarines. So Na2O2 plus CO2 converts into Na2CO3. Okay, and releasing O2. It is an oxidizing agent and oxidizes ammonia, charcoal, carbon dioxide, sulfur dioxide, and you can see if you have carbon monoxide also, it will convert into Na2CO3. If you have only carbon, charcoal, if you have, it will convert into Na2CO3 plus Na. SO2 plus NO2O2 will become Na2SO4. With ammonia, it will become NaOH and N2. Again, another important reaction. I'm marking it now. With ammonia, how is the reaction happening? Correct. So 2 NH3 plus 3 Na2O2. It is used in manufacturing H2O2 and O2, purifying submarines and used as oxidizing agent. Next, oxides of potassium K2O, K2O2, K2O3, K2O3 and KO2 and KO3. Out of all of these, the most important one are last two. One is KO2, which is bright yellow, and another one is KO3, which is orange solid, which is orange solid. Okay. K2O, K2O2, these are, hardly asked for us, so I'm not worried about these ones. I'm directly coming to this third one. Check. On treating potassium in liquid ammonia with O2 yields K2O2, K2O3, and KO2. Okay. So when you use liquid ammonia and add O2 into it, so you will get all this variety of oxides. KO2 reacts with water and produces hydrogen peroxide and O2. Okay. This one has been a very, very important reaction. So remember, as you add it to water, we'll get H2O2 as well as O2. KO3, which we call it as KOH plus O3. This is called ozonized oxygen. So at an extremely low temperature, it will convert into KO3. This is a dry powder added to ozone. So that will convert into KO3 and orange solid. Remember the oxidation state here is K plus and this is an ozonide ion, which is O3 minus. Okay, this is orange solid. Halogen's solubility down the group will always increase for fluorides. Got it? And for iodides, it will decrease down the group, it will decrease for iodides. Okay, this is the first solubility part which you need to know. And lithium halides are predominantly covalent, so they are also soluble in, they are mainly soluble in acetone. Okay, so these halogens are mostly soluble in acetone. Okay. Next, oxo acids. Check out what are the salts of oxo acids. So that includes, sulfates, carbonates, and so on. Check out first. Thermal stability decreases from top to bottom for all the bigger size anions. That includes carbon dioxide, carbonate, sulfate, nitrate, everything. So Li2CO3 will convert into Li2O2 plus CO2 plus O. Right? Sorry, Li2O only here. Li2O, CO2, and O2. Okay. While sodium, potassium, rubidium, cesium, carbonates on heating, they will give nothing because they are thermally very, very stable. Got it? At least not up to 700 degrees centigrade. Up to 700 degrees centigrade. Next, lithium nitrate. That on heating will give you Li2O, NO2, and O2. Okay. Please learn to balance this reaction also. I gave you in the notes as well. It is in the NCERT as well. So please learn that this reaction is important. LiNO3, how it will give you Li2O and NO and O. Okay. While if you notice the sodium nitrate or sodium or all other metals on heating, they will give you Na, NO2 plus O2. Okay. So if we take 2 moles of this, 2 moles of this plus O2. Okay. So they directly does not give NO2. They will first give you O2 on heating. Solubility of carbonate, bicarbonate, sulfate, and sulfite that increases down the group. So generally, we expect that this is the exception which you will notice. So down the group, if you notice that metal carbonates or metal bicarbonates or sulfates or sulfides, they all will increase their solubility down the group. Okay, this is an exception. So anomalous behavior, you will notice that lithium will have high melting point, it will have high boiling point compared to the other elements. Okay. It will form only oxide and nitride, unlike other metals. It will crystallize with a hydride of forming, LiCl dot 2H2O, unlike other elements. Bicarbonates of lithium are not found in solid state. So on, you can see this is the balanced reaction which I wrote here. So this is how it will decompose when it comes to nitrates, while other metals will decompose in this manner. Okay. Only lithium in the group forms ethanide, right? With the ethyne formation. Okay. So you can see that. So this will form Li2C2. This will form Li2C2 directly. Okay. Both lithium and magnesium are hard and lighter than the other elements in respective of the groups. Both forms nitrate with air and their oxides are less soluble in water and they do not form sulfur oxides. Carbonates of both elements are thermally less stable. Both forms alcohol soluble chlorides. Okay, this is the similarities between lithium and magnesium. All right. Now you see how to make washing soda, which is Solvay's process. Solvay process quickly we'll understand based on the equations, right? Based on the given equations. See, you are supposed to take ammonia, add it with carbon dioxide in water, so that first you can generate ammonium carbonate. The ammonium carbonate, as you add it with excess of carbon dioxide, will become ammonium bicarbonate. And ammonium bicarbonate, when you add it with NaCl, will form ammonium chloride and sodium bicarbonate. That's how we are getting sodium bicarbonate in the first case. Okay. And sodium bicarbonate, on heating, we will get sodium carbonate, Na2CO3, here, CO2 and H2O, right? And ammonium chloride, which has been released, right, will be recovered adding with calcium hydroxide. Calcium will form calcium chloride. Ammonia will convert, ammonium chloride will convert into ammonia. So that's how this ammonia is again recycled back. And here we are getting Na2CO3, correct? And out of these cases, what you need to understand is that NaHCO3 here is insoluble. That's why we are able to separate with ammonium chloride. That is the important part of Solvay process. Okay. Which we can't do it for, K2CO3 because its bicarbonate is very much soluble in ammonium carbonate. Okay. So that's why for potassium it cannot be used. For sodium, this is the reaction used. So I would suggest all of you to write and learn this. Okay. Make sure that you will write it multiple times and learn it. Okay. Not now, but I'm sure you have the equations. So please check it out once. What is Solvay process and see what is the important conditioning. Na2CO3 is white crystalline solid. Okay. On heating, it will, uh, release out the water, right? And you will get Na2CO3 plus H2, Na2CO3 dot H2O here, okay, which will convert into this 10 moles of H2O. And Na2CO3 dot H2O, sorry, here it is dot, Na2CO3 dot H2O becomes completely anhydrous and changes to white color powder called soda ash at 373 kelvins. Okay, above 373 kelvins. So it will become Na2CO3 plus H2. It is used as laundering, softening, and cleaning purposes. Okay. It is used for borax glass and caustic soda. It is used in paper, paints, textile industry. Important reagent for quantitative and qualitative analysis. NaCl comes mainly from seawater. It contains 2.7 to 2.9% by mass of the salt. It is used as common salt. It is used as utilized for preparation of Na2O2 and Na2CO3. It is prepared freezing mixture of laboratory and it is common reagent for melting ice and snow on roads. Okay. NaOH. NaOH is mainly prepared from, methods like Kastner-Kellner method. How is it prepared? You can see we can use it using Kastner-Kellner method where we use mercury as the cathode and carbon as the anode here. Okay, with NaCl, which is brine solution. On the cathode, sodium will get reduced only if the mercury is the cathode, and Cl minus will get oxidized to form Cl2. Okay, amalgam with H2O gives sodium hydroxide and hydrogen gas. So when you add this to H2O, it will give NaOH and mercury will be out and giving H2 gas. So what is left is OH minus is already present in the solution, okay, which is formed by this one, and Cl2 has been released as gas outside. Okay, so eventually the product will have H2, Cl2, and NaOH. These are the products which you will have eventually when NaCl is added to water and hydrolyzed and electrolyzed. Sorry. Melting point of NaOH is 591. It is highly soluble in water and gives strong alkaline solution. Okay. Crystals of NaOH are deliquescent. And it reacts with carbon dioxide wherever there is surface available and forms Na2CO3. Okay. Mainly used in manufacturing of soap, paper, artificial silk, and number of chemicals, and in petroleum refining, and so on. NaHCO3, baking soda, right? If you take Na2CO3 and add it to excess amount of carbon dioxide, baking soda is formed. It leaves bubbles of carbon dioxide, making the cake fluffy, and NaHCO3 is mild antiseptic for skin infections. Okay. Next, check out group 2 metals here. Group 2 elements includes beryllium to radium. Now, general configuration is this. It will have NS2 configuration. So, beryllium 2s2, then 3s2, 4s2, and 5s2, and so on. Okay, this is the general configuration. And if you compare, few things here, atomic size increases down the group, right? And ionization decreases down the group, right? Hydration energy decreases down the group. Beryllium will have exceptionally high hydration energy. Okay. And ionic radius, metallic radius, everything increases down the group. So there is no, everything has a regular trend here. Now notice the melting point. Melting point is important. When it comes to melting point, generally we expect this to decrease down the group, isn't it? We expect this to decrease down the group, but you can see magnesium is low initially, but after that for calcium it increases, again for strontium it decreases, for barium it decreases, and then radium. This is what you'll observe. So basically, in case of melting point, you'll notice that beryllium is greater than calcium, greater than strontium, greater than barium, greater than magnesium. So this is one important deal of melting point. Next, when it comes to boiling point, you will see again a similar trend here with beryllium exceptionally high, then barium, got it. After that, we have calcium, strontium, and magnesium. Okay, this is melting point and boiling point case. Density also in a similar lines here. So you will see the first three density is decreasing and then density is increasing thereafter. Okay. Standard reduction potential, if you notice that down the group, right, it will supposed to, even in group one, it is supposed to increase, but lithium was far better. Unlike that, here there is a regular increase in the trend. So barium will have the highest standard reduction potential, right? Highest negative standard reduction potential, then strontium, then calcium, magnesium, and then beryllium. Ionization, hydration enthalpies, physical properties, I'm sure these are all clear. Now, notice this one, beryllium and magnesium grayish in color. They have small size as compared to the first group, but relatively high melting and boiling point. Their low ionization makes them, you know, their low ionization makes them high electropositive, yet they are less electropositive compared to the first group. Okay. Now, when it comes to flame test, this will give brick red, crimson red, apple green. Beryllium and magnesium do not impart any color; they'll just shine. Okay. Reactivity wise, alkali metals will have more reactivity than alkaline earth metals. Okay. Now remember this one, reactive towards air. Beryllium magnesium forms oxides and nitrides, strongly, while calcium strontium forms oxides easily. Got it? Now notice this one, readily attacked by air to form oxides and nitrates here also. Got it? But when it comes to magnesium and beryllium, okay, they react much stronger than this to form the respective nitrates and oxides. Reactivity towards water, as metal added to water, it will also give you H2 gas here. Okay, so now this is an important point. Beryllium is inert towards water, and magnesium also reacts, but only with hot water, not with cold water. Okay, next, there is a protective layer formed, makes magnesium less reactive towards water unless layer is removed, amalgamated with mercury. Others metal reacts readily. Okay. Next, reactivity towards halogens. They all react easily to form metal halides. Now you see thermal decomposition of this is the most efficient route for formulation of BeCl2 and BeF2. Okay, and made conveniently from oxides. Okay, so this one, ammonium, beryllium fluoride, that will give you more easily with BeCl2 and BeF2. See what you can see, BeO plus carbon plus Cl2 at high temperature, that will give you BeCl2 more easily. Okay. BeCl2, when you react with lithium aluminum hydride, right, will form BH2, forming LiCl and AlCl3. Okay. An important reaction here. Next, reactivity towards the acid here. If you notice, magnesium when you treat with HCl will form MgCl2 and H2. While if you notice beryllium being amphoteric with NaOH, it will form with excess of first it will form BOH2 and excess it will form this complex. So beryllium will have the amphoteric nature, so to form this complex. Reducing nature, I told you that down the group it increases. Again, solution in liquid ammonia is important part. See, when metal is added to ammonia, this will also get ammoniated. Unlike one electron, this time there is two electrons ammoniated. Because more number of electrons are present, it will give you deep blue color, deep blue black color. Okay, got it. So from the solutions of ammonites, these complexes can be regained. That is 6 moles of ammonia will be forming a complex, and that's how we can get it as a complex. Okay, and this is more valid for calcium, strontium, and sorry, magnesium, calcium, strontium, and barium. Okay, beryllium doesn't give this kind of complexes. Next, Beryllium, it is mainly used in manufacturing of alloys. High strength are made used for copper beryllium alloys. Windows of X-ray tubes used, by metallic beryllium. Magnesium is a range of alloys with zinc, aluminum, and tin. Okay, it will form magnesium aluminum, alloys as aircrafts here. Next, magnesium powder is utilized in flash powders and bulbs, right? And incendiary bulbs and signals. A suspension of MgCO3 is no, which we call it as milk of magnesia, utilized in antacid. MgCO3 is an ingredient in toothpaste as well. Okay, these are few uses for magnesium. Calcium, I'm sure you can read this and complete it. Radium salts, used for radiotherapy and treatment of cancer. Notice the compounds of metal hydroxides here. Sir, in notes you gave magnesium. Can you explain liquid ammonia case once again? Okay. See, in liquid ammonia, metals would form these kind of, you know, ammonia complexes. Okay. As much as uh, solution is concerned, the deep blue black solution is mainly obtained by calcium, strontium, barium. These three will give you that deep blue black coloration when you add it to ammonia. Okay, because of the ammoniated electrons. And over the period, we can actually make these compounds, right, into, we can gain them as complexes, which means it becomes difficult to separate them. They'll become very stable complexes. In that, magnesium, calcium, strontium, barium can play a role. Magnesium, not so much formation of this hydrides beta, but it can form the complex, is what I'm saying. That means it can have a complex formation, not directly, but it can have this kind of complex formation. Clear? May not be directly reacting with metal with ammonia. Okay? If that is a confusion, let me remove that from here. It is this something which it can form. Okay? Satvik, clear, beta? Yes. Next, when it comes to hydroxides here, these are the hydroxides. Solubility increases down the group, in which beryllium hydroxide, being amphoteric, reacts with both acids and bases. Okay. So solubility, thermal stability, and basic nature, they all increases down the group. Okay. Now, if you notice, as a reaction with beryllium is important. Notice that what is the reaction that happens? HCl with BOH twice and BOH twice with OH minus is the hydroxide which is formed. Next, halides. If you notice halides here, MX2 are ionic except for BX2. They are covalent and soluble in organic solvents. BeCl2 has a chain structure in solids. Right. This is how the structure would be. BeCl2 vapors form dimer, which dissociates into linear monomer at high temperatures of the order 1200. Okay. MgCl2, CaCl2, SrCl2, and BaCl2, if you notice, tendency to get hydrated decreases down the road. Okay. Tendency to get hydrated decreases down the road. Okay. Much. Mainly magnesium forms MgCl2 dot 6H2O. Okay. Well, it will have all the ranges, but I think it is 6H2O is what observed the most. I think in NCRT 6H2O is only given, right? Everybody. There was some confusion with 8H2O, but it is not the case. Usually it is 6H2O. Right. 6H2O. Let me just confirm. I'm just checking in the NCRT.
Sir,
Hmm.
in NCERT 1 case they gave 8 H2O, in
8H2O.
other case
Just checking
6.
that. Tendency to form halide hydrates gradually decreases, correct? And this is given 8H2O dot 8H2O. Rest of these given as 6H2O, and this one is 2H2O. Right. Okay. If it is been asked the range is 1 to 12. Okay. 1 to 12 H2O can be formed for magnesium. Right. Next. Let's see carbonates. Metal carbonates are generally insoluble in water. Down the group, their solubility decreases, thermal stability increases. On heating, they release carbon dioxide, all of them. BCO3 is unstable and can be sustained only in carbon dioxide atmosphere. White solids, sulfates are white solid, thermally stable due to large hydration. Beryllium and magnesium both are readily soluble in water, while solubility decreases down the group. Calcium sulfates, calcium to barium, they are insoluble. Nitrates, carbonates, their carbonates with nitric acid will give nitrates, decreasing hydration tendency down the group, crystallizes with 6 molecules of water, whereas barium nitrate crystallizes as the anhydrous salt, just like lithium nitrate, all of them will decompose on their uh, oxide forms. They'll decompose into their oxide forms like this. I guess this part is clear, everyone. Yeah. Abnormal behavior of beryllium, you can see. While other members, this is important, rest all you can know that. Other members exhibit, you know, number of six coordination number. Beryllium usually exhibits only four, okay? Because it has only four available orbital for bonding. Beryllium shows amphoteric oxides and hydroxides, unlike others. Beryllium shows similar property to Al plus 3. Okay. And beryllium hydroxide dissolved in excess of base to produce berylate ion, just like aluminum hydroxide produces aluminate ion. Both form bridged covalent chlorides soluble in organic solvents. They both have common catalyst in Friedel-Crafts reactions. Check out these compounds. First, calcium oxide, calcium carbonate on heating with rotatory kiln that will produce calcium oxide. This is commercial way of preparing CaO, and you can see that CaCO3 reacting heating to give CaO. CO2 is taken as soon as it is produced to ensure there is no backward reaction. CaO reactions are it will react with water to form hydroxide. It will react with carbon dioxide to form calcium carbonate. It will react with silica to form calcium silicate and phosphate to form calcium phosphate. Okay? It is more like an acid-base reaction. This is a flux reaction, right? This is basic flux, acidic flux, and forming of slag. These are slag formations. Okay. That's why it is mainly used. It is important material for manufacturing of cement and cheapest form of alkali. It is used in the manufacturing sodium carbonate for caustic soda. Next, calcium hydroxide is made by adding water to quicklime of CaO. It is a white amorphous powder, sparingly soluble in water. Its aqueous solution is lime water, and a suspension of slake lime is called milk of lime. Calcium hydroxide plus carbon dioxide will give calcium carbonate precipitate, and on passing excess of carbon dioxide, it will become bicarbonate, which is soluble and that get dissolved. Milk of lime reacts with chlorine to form hypochlorite, and a component is called bleaching powder. And when you react with chlorine, this will become CaOCl twice, which is what we call it as bleaching powder. Okay. Used in building material, whitewash due to disinfectant, is used in making, glass, tanning industry, purification of sugar. Everything is the same lines again given in NCRT as well. Okay. Next, if you notice calcium carbonate here, okay, it can be found by reacting with calcium hydroxide or directly reacting with Na2CO3. So to form NCaCO3. That on decomposition gives CaO. On reacting with HCl becomes CaCl2 releasing carbon dioxide, H2SO4, calcium sulfate and CO2, all with dilute acids. Okay. Uses, sorry, just now we discussed manufacturing of quicklime, important for flux, removal of acidic impurities from ores, manufacturing high quality papers, especially precipitated calcium carbonate in extensively, used as an antacid, mild abrasive in toothpaste, a component for chewing gum, and a fillers in the cosmetics. Calcium sulfate, you know, hemihydrate, which is, half of H2O, is what we call it as the plaster of Paris. When gypsum, CaSO4.2H2 is gypsum, on heating will give you this form, which is at 393 kelvins, correct? At 393 kelvins, if you heat it, it is what we call it as gypsum. At 393 kelvins, water of crystallization evaporates and the anhydrous calcium sulfate is produced, known as dead bonds plaster. It is has an extraordinary property of setting with adequate amount of water, making it tough, solid in 5 to 10 minutes. In building industry for plaster, it is used in immobilizing the affected parts of the fractured bones, and it is used as a molds for ornaments also. Okay, clear? Another thing which you need to understand, as much as this, say, POP is concerned, oh no, we have already discussed that. What is dead bond plaster? Check out cement. Cement, a Portland cement, it is first introduced in England. Later on, this will have all these compositions. Okay. The average configuration of Portland cement. This composition you have to mug up. Okay. Earlier also there was a question asked during, while we were discussing this topic. So please learn that. What is the composition? Now this is important. The ratio of SiO2 and aluminium must be between 2.5 and 4 for a great quality cement. The amount of CO to the sum of all the oxides here should be around twice of it. The basic materials for the manufacturing of cement are limestone and clay. While clay and lime are strongly heated at once, they fuse and react to form something called cement clinker or cement clinker. This clinker is mixed with 2 to 3% of weight of gypsum to form cement. Thus, important components present in Portland cement are tricalcium silicate, dicalcium silicate, and tricalcium aluminate. This is the main composition. So 51%, 26%, and 11%. The setting of cement, not setting of cement. When it is mixed with water, it will become a tough mass. This is expected to be the hydration of the molecules and their rearrangement. The purpose of combining gypsum is to only slow down the process of setting of cement so that it gets, suitably hard. Cement come from a commodity. This is all common thing which you can read it off. Next, biological significance. An adult body includes 25 grams of magnesium and 1200 grams of calcium compared with only 5 grams of iron and 0.06 grams of copper. And the daily intake for our body is around 200 milligrams to 300. And all enzymes that use ATP in phosphate transfer involving magnesium as the cofactor. Okay. Just like in, you know, plants also. The most important pigment for the absorption of light is chlorophyll, which includes magnesium. 99% of the body calcium is existing in the form of teeth and bones. The calcium concentration in plasma is measured at around 100 milligrams per liter. It is kept by two hormones, parathyroid and calcitonin hormone. So these are the two hormones which will maintain the calcium. So I hope all of you got an idea about what all things you need to study from this topic. Do not go anything more than NCRT. Okay, everything that would be asked will be in the lines of NCRT only. If there are extra questions, bring it to me. We'll discuss it. But otherwise, just finish up whatever the part that is there in NCRT and uh, finish the working of that today itself. Sir will give you group 13 assignment today. Meanwhile, as much as this topic is concerned, it should not be a big concern considering what all things there are in this topic. Okay. So there are hardly like 5, 6 important equations. Read them and rewrite. Please rewrite, especially Solvay process, Kastner-Kellner process. Got it? Rewrite what are the complete reactions in it and start working out on the questions given. First finish the assignment, then go to PYQs. That's my suggestion. Directly do not get into PYQs. There are less number of PYQs from this topic as it is been observed. Okay.